on that the correlation, the association between both of these variables is being reported as 0.880. Okay? We could have explored that as well graphically. And in one of my previous videos, I detailed how to generate a scatter plot for an independent and a dependent variable. But let's actually just have a look at a scatter plot for these 474 observations. Yeah, these 474 paired observations. So if I go to graphs, legacy dialogues, scatter dot plot, okay, simple scatter plot, and what I can do here is I can define my y-axis, my dependent variable, and I can define my x-axis, my independent variable. My x-axis typically represents what happened before, and the y-axis what happened after. Okay, so well, the previous, or sorry, let's say our beginning salary was something that was before our current salary, so that should be our x-axis, and our current salary is our y-axis. So let's see what happens here, just from a graphical perspective. So when we hit OK, you can actually see that there seems to be a positive trend here. Okay, what we're really saying is this positive trend seems to be suggesting that small salaries or small beginning salaries are associated with small changes in current salary. Large beginning salaries are associated with large changes in current salary. Okay, if we double click on this, we can put the line of best fit in there, and we can actually see that this line of best fit is I suppose, I won't say significantly positive. It has a very large slope, okay, which is I suppose from a graphical and descriptive perspective, yeah, that supports what we've seen from an inferential perspective over here in relation to the correlation. Okay, so maybe just one thing to keep in mind here is that there's a number of preconditions associated with the vast majority of tests, and especially these parametric tests that we undertake. And one of the preconditions for a paired samples t-test, okay, is that the samples, the before and after, okay, that the samples have been drawn from populations that are normally distributed, okay, or that are symmetrical and bell-shaped in some way, yeah, and in particular are normally distributed. So for us to trust this particular result here, these particular samples should have been drawn from normally distributed populations. So let's just actually have a look at that. Okay, are these samples normally distributed? Is the current salary, okay, variable, is it normally distributed? Is the beginning salary variable normally distributed? Now we could have a look at this graphically. Okay, we could do histograms, go to graphs, legacy dialogues, do a histogram. If we do a histogram for, let's say, beginning salary, okay, and let's just hit OK on that, you can actually see that this, it doesn't look normal. It looks like it's positively skewed. Yeah, we could double click on the graph. We could plot a bell-shaped curve on top of that just to give us a reference point. And you can actually see that we are actually deviating significantly from normality here. Well, what seems from a descriptive perspective to be deviating from normality. So this seems to suggest that we're violating one of the conditions. What about in relation to current salary? Once again, if we do a histogram for current salary, we get rid of the variable, let's put in current salary in here. Okay. What we get here is we get, once again, you can sort of see we have a positively skewed distribution. Double clicking on it, putting a bell-shaped curve on it, and what we can actually see is, once again, we're above the curve, we're below the curve, and so on. It doesn't seem to be normally distributed. Let's do this a bit more rigorously using an inferential test. Okay, so I want to just test now, not from a descriptive perspective, not from graphs. I want to test whether there actually is evidence to suggest that we have a deviation from normality for both of these particular samples, for the current salary and also for the beginning salary. So there is a way we can do this. We can go to Analyze. I have got a video on how to test for normality as well, but we can go to Analyze. We can go to Descriptive Statistics, we can go to Explore, okay? And what we can put in here is the variables that we want to test, okay, as our dependent list. I can just run it for current salary if I like, but actually let's run it also for our beginning salary, okay? So I really want to test whether both of these are normally distributed. From a statistics perspective, we have to ask for descriptive statistics by default, so let's just run with that. From a plots perspective, I don't want stem, and I could have asked for histograms here, but we don't want that. Let's just go to Normality Plots with tests. So I'm just choosing Normality Plots with tests, and let's hit Continue, and let's hit OK on this. Okay. Now, there's a lot of output here, but some of it is what we've sort of seen already: case summary table, our descriptive statistics. Actually, what might be interesting from descriptive statistics is actually looking at the skewness and kurtosis. The skewness is 2.12 for the current salary, which would indicate positive skewness. The kurtosis is 5.378, okay, which would indicate excess kurtosis. It's very peaked relative to a normal distribution. Baseline here being 3, normal distribution having a kurtosis of 3, so we're above 3 here. And similarly for beginning salary, looking from a descriptive perspective, looking at skewness, we have positive skewness, kurtosis, it's also above 3 as well. So from a descriptive perspective, we have skewness, we also have kurtosis in both distributions. That would be evidence as well to suggest deviations from normality. But actually, probably what's more important here is this output here, this box, which is tests of normality. These are inferential tests of normality. And there's 2 tests here. There's the Kolmogorov-Smirnov test, and there's the Shapiro-Wilks test. We're just going to rely on the Shapiro-Wilks test. Okay. Well, we have current salary. We have a test statistic of 0.771. Degrees of freedom is 474, and a significance of 0.000, which is less than 0.05. For beginning salary, we have a test statistic of 0.715, degrees of freedom 474, and also a significance less than 0.05. Okay? Now, the null hypothesis for a test of normality is that the distribution that's being tested is no different to a normal distribution. In other words, that they're the same. So actually, the default position here is that we assume that the distribution is normal. The alternative is that the distribution is not normal. And in both cases here, you can see that we're rejecting the null hypothesis. Yeah, okay. So actually, from an inferential statistics perspective, we have just provided evidence to suggest that the current salary is not normally distributed. Okay, and that'd be at the 5% significance level. And the beginning salary is also not normally distributed. In which case, the results of our the results of our paired samples t-test possibly should not be relied upon. Albeit our sample sizes are very large, okay, they're 474 observations. But with such deviations from normality, it'd be probably more appropriate that we ran a non-parametric paired samples test. Okay? And we'll do that next. There will be a video that we'll have a look at next that will run the same data, but this time through the alternative approach using a non-parametric test for the difference between two populations. Okay? The paired difference. Okay, guys. I hope that was somewhat intuitive. And once again, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland.